and certain control definitions. 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 Definition. Let Fn be a sequence of measurable functions definition. Let F measure let Fn be a sequence of let Fn be a measurable function. Measurable function. Fn means function. Measurable. Measurable function. And F be measurable function. And F be measurable function. Measurable function. Measurable function. We say the Fn converges to F. We say the we say the Fn converges to we say the F means this is within shape symbol means sequence. Fn converges to F. Converges to F. Fn is converges to F. For each epsilon greater than 0, measure measure epsilon greater than 0. And eta greater than 0. This is read as neta. Neta greater than 0. Neta greater than 0. There is a natural number n naught such that the natural number there is a natural number n naught estimates such that for all n greater than for all n greater than n naught n greater than n naught the inequality the inequality, the equality, mu, the equality, mu is measure, such that modulus of fn x, f, fn of x greater than epsilon, greater than epsilon, less than, greater than epsilon, then in other words, xn converges to, in other words, in other words, no, fn converges to fn, CGS means converges to f, fn converges to f. In measure, in measure, in measure, limit for each n greater than 0, n greater than 0. Limit n tends to infinity. Limit n tends to infinity. Limit n tends to 0. N tends to 0. Mu, mu, mu. X such that modulus of such that fn x minus f of x, fn x minus f of x is less than epsilon, is less than epsilon, that equal to 0. 0. This case we can write, fn tends to f. MEAS means measurable. Fn on x, measurable convergence, measurable function on x, fn to MEAS. It means measurable function on x, measurable function on x. Measurable function on x. Measurable function on x. Measurable function on x. Next, using definition, will prove a one theorem. Theorem number one, page number 82. Page number 82. Theorem number one. Statement. Theorem. Theorem. Question formation is prove that or show that. Prove that or show that. Fn is a sequence. Let Fn. Let Fn is a sequence of measurable function. Let Fn is a sequence of measurable function. Is a sequence of measurable function. Sequence of measurable function. Sequence of measurable function. In measure means measurable integration. Measurable integration. Measurable function f such that measurable function f st means such that fn tends to f. Fn tends to f. MEAS means measurable function on x, meaning proof. Proof of this theorem. Proof. Proof. Since Fn is a measured sequence in measure, since the sequence Fn is a sequence of measurable function, is a sequence of measurable function. A sequence of measurable function. Sequence of measurable function. Sequence of measurable function. Sequence of measurable function. In measure, to each integer I greater than 0. In measure, each integer I is greater than 0. Greater than 0. There is a natural number ni. There is a natural number. There is a natural number ni such that for all m is greater than or equal to ni, for all m is greater than or equal to ni, m is greater than or equal to ni, n is greater than or equal to ni, n is greater than or equal to ni. We have measure of x such that mod fmx minus fnx minus Fnx, Mnx greater than or equal to 1 by 2i, greater than or equal to 1 by 2i, greater than or equal to 1 by 2i is less than 1 by 2i, 1 by 2 to the power of equation number 1. Equation number 1. So we may assume that Ni equal to 1 to n. We may assume that we may assume that Ni equal to 1 to infinity. Ni I equal to 1 to infinity. I equal to 1 to infinity is an increasing sequence of natural numbers. Is an increasing sequence of increasing sequence of increasing sequence of natural numbers. Increasing sequence of natural numbers. Natural numbers. Increasing sequence of natural numbers. That is Ni plus 1. That is N I plus 1 is greater than or equal greater than Ni. Greater than Ni. For I is greater than or equal to 1. I is equal to greater than or equal to 1. If Ei equal to if Ei x such that Fnix minus modulus of Fni x minus Fni plus 1 I plus 1 x greater than or equal to 1 by 2i, greater than or equal to 1 by 2 power I. 2 power I. It follows that one. It follows that it follows that it follows that one that one mu of ei mu of ei mu of ei less than 1 by 2i for I is greater than or equal to 1. Also, if x does not belong to also if x does not belong to union of I equal to m to infinity ei, union of I equal to m to infinity ei 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 yeah. R greater than s less than or equal to m. R greater than or equal to s is greater than or equal to m. The value of s is lies between r and m. Then we have modulus of fnr x minus FNS. 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 X. FNS. X. FNS. X. FNS is less than or equal to sigma. Sigma I equal to S plus 1. I equal to S plus 1. S plus 1 to R. Plus 1 to R. FNR modulus of FNR X minus modulus Fni plus 1 of X X is less than sigma I equal to S plus 1 to I equal to S plus 1 to R. Where what is the S here? S is lies between R and M. R and M is less than sigma is less than 1 by 2. It is 1 by 2 is less than I S plus 1 to infinity. I equal to S plus 1 to infinity. 1 by 2i. 1 by 2i is less than 1 by 2 to the power of S. 1 by 2 to the power of S. This is equation number 2. Equation number 2. Next. So that Fnix is a Cauchy sequence. So that Fnx is a Cauchy sequence. Fnix is Cauchy sequence. Cauchy sequence is a Cauchy sequence. Fnx is a Cauchy sequence. X does not belong to intersection M equal to 1 to infinity. M equal to 1 to infinity. That means union of I equal to 1 to infinity EI that equal to capital A flat or say flat. But M of A equal to what? Mu of A. Mu of means measurable function of A. Mu of A equal to mu of intersection M equal to 1 to infinity union of I equal to M to infinity is less than or equal to mu of union I equal to M to infinity EI M to infinity EI for all M is less than or equal to I equal to M to infinity equal to 1 to infinity mu of EI mu of EI is less than sigma I equal to m to infinity, I equal to m to infinity, 1 by 2i, 1 by 2i, 1 by 2. That equal to 1 by 2 to the power of m minus 1, to the power of m minus 1, for all m, for each m, showing mu of a equal to 0. Showing mu of a equal to 0. Mu of a equal to 0. N tends to infinity. 1 by n tends to 0, no? That's it. This is m to infinity. Mu of 0. Thus, F1 is convergence almost everywhere. Thus, F1 converges. F1 converges. F1 converges almost everywhere. Some measurable function. AE means almost everywhere. Some measurable functions. M functions means FNS means measurable functions. Measurable functions. F is also who shows Fni is sequence. Second equation shows second equation shows Fni is converges, which is fundamental uniformly. Fni. CGS means convergence. Fundamentally uniform. Fundamentally uniform. Fundamentally uniform. Fundamentally uniform. On complement of set. Uniform on complement of set. On complement of the set. Complement of the set. Complement of the set. Union I equal to 1 to infinity. Union I equal to m to infinity. EI set EI for each m for all m. Fni tends to F uniformly on complement. Therefore, Fni tends to F. Fni tends to F uniformly on complement of uniformly on complement uniformly on complement of union I equal to 1 to m to infinity. Union I equal to 1 m to infinity. EI yeah. and hence and hence and hence for all epsilon greater than 0, epsilon greater than 0 and greater than 0. So mu of mu of x such that mod fni x minus mod fni x fni x minus f of x minus f of x f of x less than epsilon by 2 less than epsilon by 2 tends to 0 is tends to 0 as I tends to infinity as I tends to infinity. Equation number 3, third equation. This is important for 10 marks. Now since x such that mod fn x mod fn x f of x mod fn x minus f of x greater than epsilon is subset or equal is subset x such that x such that that's it fn x minus fni of x modulus of fn x fn fn x fn x minus fni of fn of x greater than epsilon by greater than epsilon by 2 greater than epsilon by 2. Union x such that modulus of f of x minus fni of x is greater than epsilon by 2 greater than epsilon by 2 greater than epsilon by 2 greater than epsilon by 2. So we get uh, we get mu of x such that mu of x such that modulus of f of n x fn x minus f of x greater than epsilon is less than or equal to mu of mu of x such that mod fn x So fnx minus f of nix f of nix modulus of epsilon by 2 epsilon by 2 epsilon by plus your union means plus mu of x such that mod f of x mod f of x f of x minus fni of x fni x squares mod epsilon by 2 greater than epsilon by 2 epsilon by 2. So Fn is fundamental measurable, hence here since Fn is fundamental, is a measure, is a fundamental, fundamental, fundamental is the fundamental is measure the first term is measure the first term measure the first term on right is arbitrarily small RHS means right hand side is arbitrarily small arbitrarily small by 3 second term is arbitrarily small arbitrarily small second term arbitrarily small arbitrarily small. So hence Fn tends to hence Fn tends to F is measurable MEAS measurable function. This completes the proof, hence proof important for 10 marks. Hence proof. Next. Definition. 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 Let Fn be a sequence of measurable function. Definition. 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 Let Fn be a sequence of measurable functions. Let Fn be a sequence of measurable functions. Sequence of measurable functions. And F be a measurable function. F be a measurable function. Measurable function. We say that Fn tends to. We say that Fn tends to F almost uniformly. Fn tends to F almost uniformly. Almost uniformly for all epsilon greater than 0 or for each epsilon greater than 0. There is a set E. There is a set E such that mu of E less than epsilon less than epsilon less than epsilon and Fn tends to Fn tends to F Fn tends to F uniformly on x minus E. X minus E. In this case, we write. In this case, we write. Fn tends to F. Fn tends to F. AU means almost uniformly convergence, meaning based upon this definition, theorem number 5 for short answer question. For short answer. For short answers, for short answer questions. Important. Short answers. And the 6 is also short answer. Theorem number 6 is also Short answer. Post two dash form. Next, unit 9, measurement topology. Unit 9, measure and topology. Unit 19. Unit 9, 19, measure and topology. Measure and topology. Measure and topology. Concepts. And definition. Concepts and definitions. Concepts and definitions. Concepts and definitions. Topology preliminaries. Definition. Topology preliminaries. Definition 1. A collection tau of subset of X. A collection tau of subset of X. Tau of subset of X. Subset of X. Tau of subset of X is said to be topology. Is said to be topology. TP means topology. Topology. If tau has the following properties. If tau has the following properties. Following properties. Following properties. First one. Phi belongs to tau. Phi belongs to tau. And X belongs to tau. And capital X belongs to tau. Second, if G alpha is an arbitrary collection of members, if G alpha is an arbitrary collection of members, is an arbitrary collection of arbitrary collection of members. Arbitrary collection of members. Arbitrary collection of members of tau, then their union of tau, then their union, then their union, then their union, G alpha, G alpha is also a member of tau, is also a member of tau, member of tau, member of tau, and G1, G2 belongs to tau if G1, if G1, comma, G2 belongs to tau, belongs to tau, then G1 intersection, then G1 intersection, G2 belongs to tau, G2 belongs to tau, intersection, G2 belongs to tau. Tau. Your definition, one more definition we are discussing. Definition, second definition. If tau is a topology on X, tau is TP means topology on X. Tau is a topology on X. Then X tau is called topological space. Then X comma, then X comma, tau is topological space. TP means topology, SP means space, topological space. The members of tau are called, then, the members of tau are called, members of tau are called members of tau are called open sets in topological space. Open sets in topological space. Open sets in topological space. X comma tau. X comma tau. So, using this definition, we'll prove one theorem. Theorem. That is theorem number 1, page number 91. Page number 91. Prove that theorem. Question formation is prove that, show that X is a topological space. Prove that or show that let X is there. topological space. Topological space. K is a compact subset of X. K is a compact subset of X. Subset of compact subset of X. And F is the closed subset of K. And F is a closed subset of K. 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 Then F is compact. Then F is CPT means compact. Proof. 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 If G alpha is open cover of F. If G alpha is alpha is open cover of F. Open cover of F. Open cover of F. Open cover of F. Then complement. Then the complement. Then complement F bar together with the collection of G alpha. Together with the collection of collection of G alpha. Collection of G alpha. Collection of G alpha. Collection of G alpha is an open cover of X. Is an open cover of X. Open cover of X. Open cover of X. And hence for K. And hence for K. Hence for K. Hence for K. Therefore, there is a finite collection. Therefore, there is a finite collection. There is a finite collection. There is a finite collection. G alpha 1, comma, G alpha 2, etc. G alpha n. G alpha n. Or alpha r. Alpha r. Alpha r. That equal to F intersection F bar. F intersection F bar. F intersection F bar. Union meaning F intersection, F intersection, F intersection, G alpha 1, comma, G alpha 2, comma, G alpha R, alpha R. That equal to F intersection, okay, F intersection, G alpha 1 union, G alpha 1 union, G alpha 2, G alpha 2 union, etc. G alpha R, alpha R, alpha R is subset G alpha n, G alpha 1, G alpha 1 union, G alpha 2, G alpha 2, union, etc. G alpha R, union, G alpha R, G alpha R. Yeah. Is subset R, is subset of, is subset of G alpha 1, union, G alpha 2, union, etc. Union, G alpha R, alpha R. Thus F is compact. Thus F is compact. Thus F is compact. F is compact. Next, definition 7. Yep. Yes, correct. Thus F is compact. Discuss one more definition. That is definition number 7. Definition. Definition. The topological space X is said to be a topological space is said to be a topological space. Yeah, it is said to be a topological space. X is said to be a Hausdorff space. One, a Hausdorff space. A-U-S D-O R. Page number 91. Same page number. Hausdorff space. If P belongs to X, Hausdorff space. If P belongs to X, if P belongs to X, Q is also belongs to Q is also belongs to X. Q belongs to P belongs to X and Q belongs to X. And P is not equal to Q. And P is not equal to Q. Not equal to Q. then P has a neighborhood of G. Then P has a neighborhood of G. Neighborhood of G. Q has a neighborhood of H. Q has a NBD means neighborhood. NBD means neighborhood of H. Neighborhood of H. Neighborhood of H. Such that G intersection H, such that G intersection H is a null set. Is called R space. Second one, a topological space is said to be locally compact. Locally compact. If every point of x, every point of x, every point of x has neighborhood as NBD means neighborhood whose closure is compact, whose closure is compact. CPT means compact. Whose closure is compact. Whose closure is compact. Using these definitions, we'll prove one theorem. Page number 92. Page number 92. Short answer type questions. Important for short answers. Theorem. Please prove that or show that K alpha is a collection of compact sets. Prove that question formation is prove that or show that. Prove that or show that. If K alpha is a collection of compact subsets, if K alpha is a collection of, if K alpha is a collection of compact, CPT, compact subset of Hausdorff space, subset of Hausdorff space, SP means Hausdorff space, with intersection K alpha equal to null set, with intersection K alpha equal to null set, then some finite subcollection of subcollection of finite subcollection of K alpha has empty intersection of K alpha has empty intersection has empty intersection empty intersection K alpha is empty intersection. Proof. Proof. Fix a member K beta. Fix a member K beta. Fix a member K beta of K alpha. Fix a member K beta of sequence K alpha. Sequence K alpha by hypothesis and means given data. Right? The given data. Hypothesis. 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 K beta intersection. K beta intersection. Intersection K alpha. Intersection K alpha. K alpha. Equal to null set. Equal to null set. Showing K beta subset. Showing K beta subset. K beta subset. K beta subset. Union of K beta subset. Union of alpha is not equal to beta. Alpha is not equal to beta. K bar. K bar. K alpha. Is a compact set of K beta. Thus intersection of K alpha bar. Alpha is not equal to beta. Alpha is not equal to beta is an open cover for the compact set. Is the open cover for compact sets. Open cover compact set. Compact set KB. Open cover compact set KB down. Therefore, we can find. Therefore, we can find. Therefore, we can find alpha 1, comma alpha 2, comma etc. Alpha R. Alpha R. Alpha R. None of which is not equal to beta such that K beta. What's that? K beta subset K alpha 1 bar union K alpha 2 bar alpha 2 bar union etc. K alpha R union. So K alpha 1 intersection K alpha 1 intersection that equal K alpha 1 intersection alpha 2 intersection that equal to K alpha 1 intersection K alpha 2 intersection so on intersection K alpha R alpha R N can put in R which follows which follows or which shows which shows K beta intersection K beta intersection K alpha 1 intersection K alpha 2 intersection so on K alpha n intersection K alpha n that equal to null set. Hence proved. This complete is the proof. Hence proved. So, yes, students, uh, we discussed 2 units. These two are most important for short answer questions. Thank you very much.